Welcome back. We're going to continue our applications of logarithms using a carbon dating question, and we'll work with Newton's law of cooling. So here we have a carbon dating question where an archaeologist believes that a fossil is around 4,500 years old. He determines the sample contains 60% of its original amount of carbon-14, and the half-life of carbon-14 is 5,730 years. Is the estimated age of the fossilized bone correct? Well, we'll use our formula y equals a times 1/2 raised to the x over 5,730. So our half-life is our denominator here, x would be the number of years, y our ending amount, and a is our beginning amount. So we have 60% of our beginning amount, which is 1, which we would normally not write, 1/2 raised to x over 5,730. And we want to solve for x. So we will have to log both sides, and I'm going to log 1/2 both sides because I have a half-life here. So I'll do log base 1/2 on both sides. So I get log 1/2 of 0.6 equals log 1/2 of 1/2 raised to the x over 5,730. So I can bring my exponent down in front, and I end up with log 1/2 0.6 equals x over 5,730, all multiplied by log base 1/2 of 1/2, which is just 1. I'm running out of room. So that is 1, so that's going to fall out of our equation. If I multiply both sides by 5,730, I'm going to get x. So 5,730 log base 1/2 of 0.6 equals x. So I put that into my calculator, and we'll see how close the archaeologist is. So type in 5,730, math. I need log base 1/2. So log base 0.5 of 0.6. And we get 4,222.81 years. And at that, I would say our archaeologist is pretty close. That's a pretty good estimation of the age of that bone. In example 7, we're going to apply Newton's law of cooling. We've got a batch of brownies are taken out of a 375 degree oven, and it cools to 150 degrees after 20 minutes in a room that's 70 degrees. Use the law of cooling to determine how long it will take the brownies to cool to 90 degrees. Well, let's take a look at our given information. We've got an original temperature amount of 375 degrees, and it cools to 150 degrees after 20 minutes. So we've got a T of 20, and this is our Y value here. This 150 is a Y, or our T sub T. Our ambient temperature of the room, T sub M, is 70. So we've got 70 here, and what we need to find is K. So in this particular problem, the first thing we're going to do is, after we've identified everything, we need to find K. And then once we find K, we can reuse and with T sub T equal to 90. So the first thing we'll do is find K. We'll put everything into our equation, and then we'll start back all over again. So we have 150 equals 70 plus 150. Nope, that's not right. Our original temperature is 375 minus 70 e to the negative k, and our t is 20, so that's a negative 20k. So I'm going to subtract 70 from both sides, and I get 80 equals, and that's 305 e raised to the negative 20k. Divide both sides by 305, and I get, well, I'm going to leave it at that, 80 over 305 equals e to the negative 20k. So I got to get that k out of the exponent, so I'm going to natural log both sides. So I'll natural log this side, and I'll natural log this side. So I get the natural log of 80 over 305 equals negative 20k natural log of e. So I applied that power rule. I brought that negative 20k down. The natural log of e is 1. I divide both sides by negative 20, and I've isolated k. So natural log of 80 divided by 305, all divided by negative 20. So I've got to put that in my calculator and get my k value. So I hit my natural log key of 80 divided by 305. I close that parenthesis, divide it by negative 20. Hit enter, and my k value is 0.066914. So now that I have my k value, I can redo the problem. But now my output is 90 instead of 150. So let's see what that will look like. So this is my third step now, and I'm going to say 90 equals 70 plus 305 e to the negative 0.066914 t. So did that arithmetic, that information, the 375 minus 70 doesn't change, but now I want to find out when it's 90, I'm looking for t. So subtract 70 from both sides, and I get 20 equals 305 e to the negative 0.066914 t. Divide both sides by 305, and I get e to the negative 0.066914 t. And then I'll natural log both sides and solve for t. I'll natural log the right side, or the left side, natural log the right side. So the natural log of 20 over 305 equals negative 0.066914 t natural log of e. So when I do that, that brings that whole exponent comes down in front using that power rule. The natural log of e is 1. Divide both sides by negative 0.066914 to isolate t. And I'll put that in my calculator. All of this on the left side is going to be what t is. Let's see what we get. So the natural log of 20 divided by 305 all divided by negative 0.066914. And we get 40.71. So 40.71 minutes. So it'll take almost 41 minutes for our brownies to cool to 90 degrees. And that wraps up our application of logarithms with Newton's law of cooling and some carbon dating. And you'll get some more practice with this when I see you in class.